Howdy, howdy, this is Mr. Potter. In today's video, we're going to talk about the idea of complex numbers. We've talked a little bit about this in our Algebra 2 class, but in pre-calculus, we actually need to understand quite a bit about complex numbers because they have a large bearing on a lot of the things we're going to talk about throughout this course. So first, I want to introduce the idea of an imaginary number. So I want to consider this equation, x squared plus 4 equals 0. Now, if I had to describe this, I would describe this as a parabola. And I would describe this as a parabola that lies entirely above the x-axis. And by entirely above the x-axis, my vertex of the parabola is then going to be at the point 0, 4, and everything about this parabola is going to be completely above it. It's not going to touch this, and so we say that this has no real solutions. But let's take a look at this from an algebraic standpoint. If I wanted to solve for x, the first thing I would do is subtract 4 from both sides, and I end up with x squared equals negative 4. Now, normally, I'd look at this equation and I'd say, you know what, that makes no sense, there's no answer. But I'm going to suspend my disbelief, and I'm going to continue to solve for x. So I'm going to take the square root of both sides, and I'm going to kind of ignore the fact that the square root of a negative number is a problem. I know the square root of x squared should give me x, and I should end up with a positive and negative square root of negative 4. So I have a value for x. X is going to be one of these two solutions. Neither of them are real solutions because this graph never touches the x-axis, but I'm going to suspend my disbelief. I know that negative 4 is really 4 times negative 1. And I know that if I have a radical, then I can take a radical of a product that equals the product of the radicals. And this is easy to deal with. I know the square root of 4. The square root of 4 is 2. But then I still have the square root of negative 1, and this is irreducible. I really can't get any closer to an answer here than to just kind of say that's my answer. And this happened during the 1800s, and so mathematicians came up with this idea to let the square root of negative 1 be I. And so we would say that my solution is plus or minus 2i. And so this idea here is something called an imaginary number. So this isn't a real number, because if it was a real number, this parabola would have a solution on the real number line. I would have places where my parabola cross the x-axis. I don't. So we call this an imaginary number, but keep in mind this is a second-degree polynomial, so I should have two possible solutions, at most two possible solutions, and my two solutions are positive and negative 2i. So let's investigate this a little bit more. The idea behind an imaginary number is we're using it to describe the solutions to these types of functions. So we say that I is equal to the square root of negative 1. And so what I can do is that whenever I have something like the square root of negative 25 or the square root of negative 98, I can rewrite this. I can take this and say this is really the square root of 25 times negative 1, or the square root of 25 times the square root of negative 1, and just write that as 5i. Or I could take this and say it's equal to the square root of 98 times negative 1. And although 98 is not a perfect square, it really is 2 times 49 times negative 1. So this is 7, this is a square root of 2, and this is an I. And by the way, by convention, we tend to write this as 7i times the square root of 2 because I don't want to have to worry about did I write that little mark at the end of my radical to make sure that everything got taken care of the way it was supposed to. Now, something I want to do as an aside is I want to take the solutions. We said that x squared plus 4 equals 0 has solutions plus or minus 2i. So if I take a look at this and I try and substitute this into the equation, let's take a look at what happens when I substitute. Well, if I take the positive 2i and square it and add 4, the question is, do I get 0? Well, I know that when I square terms that are multiplied by each other, I could really say that this is 2 squared times I squared plus 4. And my question, of course, is this equal to 0? Well, this is 4, and this is the square root of -1 squared. And I know that I know that square roots and squares are inverse operations. They kind of undo each other. So I end up with -4 plus 4, and that is, in fact, equal to 0. So the positive solution checks. If I were to check the negative solution, I'm going to follow the exact same math. So I should have -2 squared times the square root of -1 squared plus 4. And my question is that equal to 0? Well, -2 times -2 is a positive 4. I know that square roots and squares are inverse operations, so that gives me a -1. And I do end up with 0. So even though it seems like I'm kind of waving my hands and saying anytime that I have a square root of -1, we're just going to call it this imaginary thing, it really does have a consistency to it that makes it really nice to work with. Now, one thing I do want to talk about real quick, we have this idea of principal roots that we talked about in Algebra 1 and Algebra 2. The idea is that if I have a problem that already has the square root in it with a number, then this is always going to be just the positive version. I'm never going to consider the negative version of this. So the square root of 9, if I see the square root of 9 with the square root symbol already done there, it's 3. The principal roots are always going to be positive roots. And it's important to remember that if the symbol is already present in my problem, then all I'm interested in is the positive solution. I'm not interested in the negative solution. However, if I had a situation where I had x squared minus 9 equals 0, and then x squared equals 9, and then I took the square root of both sides, this is where I introduce the positive or negative. The thing is, if the square root is already present, that's a principal root, and I want to go ahead and accept just the positive root. But if I have to put the square root symbol down, then I have to consider the positive and negative, and that means that I'm going to end up with 2 solutions to this. Of course, we expect that because a second-degree polynomial should have 2 solutions. A third-degree polynomial should have 3 solutions. And of course, we've had problems with that in the past because sometimes all we could find was just one real solution out of a cubic, or we could find no real solutions out of a quadratic. Well, now we see that there is another way to look at this. So just realize that if the square root is already present, that's a principal root. If the square root is not present and we have to apply the square root, then that's going to be a positive or negative square root that we're going to have in our process. So once I have this concept of imaginary numbers, we also have the concept of complex numbers. And of course, complex numbers are more complex than just being a real number and just being an imaginary number. So a complex number is the sum of a real number and an imaginary number. In other words, it's always going to be of the form a plus b times I. And this is really as close as we can get. We can't really combine like terms because they're not like terms. One number, this first part, is real. And the second part here is imaginary. And these are completely disjoint sets. We have our real numbers and we have our imaginary numbers, and they don't overlap. But they do belong in a larger set, which we call the complex numbers. And these complex numbers are going to be any combination of a real number and an imaginary number. Any linear combination, basically saying that we're adding together 2 numbers to get a different number. Now, what's important to understand is that when I'm talking about a complex number, I'm going to see something like 3 plus 4i, or 2 minus 5i, or -1 plus 6i. These are all examples of complex numbers. Technically, the 2i that we dealt with earlier is a complex number because there really is a 0 that we see in front of it. And that 0 really is our real part. And similarly, I could think of 4 as being a complex number because 4 plus no i's, I could have it now in this form. I can write any number, a real number or a complex number or an imaginary number, in this form a plus bi. And of course, it's important to observe that a real number is a complex number with a 0 imaginary coefficient. In other words, anytime I'm dealing with a real number, this part has to be 0. And a complex number, excuse me, not a complex number, an imaginary number is a complex number with a 0 real term. So in other words, if I'm dealing with a number that's purely imaginary, that means that this real term must be 0. Excuse me. So it's important to understand that although I have real numbers and I have imaginary numbers, they're completely disjoint sets. They don't overlap at all. They are all members of some larger set called the complex numbers. So my 4 is here, my 2i is in here, but a number like 3 plus 4i or 2 minus 5i or negative 1 plus 6i all lie in this outer ring, and all of these are examples of complex numbers. Now, we're going to find ourselves in the situation where we're going to need to plot a complex number. And so to plot a complex number, we have to consider the real part and the imaginary part. And when I plot a number on an xy plane, the x-axis is considered my real axis, and the y-axis is considered my imaginary axis. So if I have a number like 3 plus 4i, since my real component is 3 and my imaginary component is 4, that really means that my x component is 3 and my y component is 4, and it's going to look an awful lot like the number 3, 4. So this would be an example of 3 plus 4i. If I wanted to graph 2 minus 5i, I would go over 2 and down 5, and this is going to be 2 minus 5i. And if I wanted to do negative 1 plus 6i, I'm going to go to the left 1 and up 6. So this is going to be the point negative 1 plus 6i. Graphing these is fairly easy because all I need to do is to think of things. My real component is going to be my x coordinate, and my imaginary component is going to be my y coordinate. So plotting or graphing complex numbers is pretty straightforward. The next thing that we want to talk about is complex arithmetic. In other words, how to add, subtract, multiply, and divide complex numbers. And of course, it's convenient to remember that because we're dealing with numbers that are of the form a plus bi, think of these as unlike terms. But what we want to do is we want to combine like terms. So if I had two numbers that I wanted to add, like 3 plus 4i, that I want to add to 2 minus 5i, then I want to consider my real terms and add them together, 3 plus 2. And then I want to consider my imaginary terms and add them together, 4i minus 5i. And the thing is, all of these real terms should combine to give me one real term, and all of these imaginary terms should combine to give me one imaginary term. So 3 plus 2 is 5, and 4i subtracting 5i leaves me with a negative 1i, and so my answer is 5 plus a negative 1i, or 5 minus I. If I wanted to subtract complex numbers, I'm going to follow the same procedure. The thing that's different about it is that if I have negative 1 plus 6i, and I want to subtract 3 plus 4i. Then I'm going to do the same thing. I'm just going to be subtracting the real components, and I'm going to be subtracting the complex components from each other. So here I'm going to have negative 1 minus 3, and then here I'm going to have 6i minus 4i. And I'm going to be adding these results together to get a number of the form real part plus imaginary part. So this is going to be negative 4 plus 6 minus 4 is 2i. So adding and subtracting is very similar to what we already are familiar with adding and subtracting. The main difference, of course, is that because I have two different unlike terms, I need to make sure that I combine like terms so that I have one real term and one imaginary term. And multiplication runs very similar to that. So if I wanted to take the expression 3 plus 4i and multiply it times 2 minus 5i, well, I notice that I have binomials. And of course, I can distribute the binomials using the term we called FOIL. So multiply the first terms. 3 times 2 is 6. I've got outer terms. 3 times negative 5i is negative 15i. I've got 4i times 2 for my inner terms, which is 8i. And then I have 4i times negative 5i, which would be negative 20i squared. But keep in mind, we've talked about I squared before, because that's really the square root of negative 1 squared, and those are inverse operations, so we get negative 1. So really, this part and this part are real numbers, and this part here and this part here are imaginary numbers, and I need to combine like terms. So this is 6, and this is really negative 20 times negative 1, or a positive 20. And 20 plus 6 will give me 26. And then I've got negative 15i plus 8i. That's going to give me a negative 7i. So even though multiplying these two complex numbers looks complicated, in reality, we're using the same FOIL that we learned in Algebra 1, the same techniques that we had to multiply two binomials together. The only difference that we have is instead of having an x and an x squared part, we have an I and an I squared part. And this I squared part we deal with because the fact that I squared equals negative 1. So that's addition, that's subtraction, that's multiplication. Of course, division is the part that makes things really difficult. And in order to understand division, I need to talk about the idea of a complex conjugate. The idea of a complex conjugate is that if a plus bi is a complex number, then a minus bi is that number's complex conjugate. So in other words, if I had a number like 3 plus 4i, then its complex conjugate is going to be 3 minus 4i. And the idea for finding these complex conjugates is whatever's in my denominator, I'm going to need to find some way to get all the imaginary parts out of the denominator. And what's nice about multiplying a complex number times its complex conjugate is this really is a difference of squares type situation. So what I really am going to have is my first, my outer, my inner, and my last. So I'm going to have 9 minus 12i plus 12i, and 4i and negative 4i is going to give me a positive 16. Notice that these are additive inverses. They're going to become a 0 pair. And I have 9 plus 16, which is 25. And so what's really nice about this is that if I multiply a complex number by its conjugate, I'm going to get rid of any imaginary part. I'm going to be left with a constant that's real. So let's do a division problem. Let's say that I have 2 minus 5i divided by 3 plus 4i. So I've got a complex number divided by a complex number, and the complex conjugate of this is 3 minus 4i. Well, I can multiply this fraction by a clever form of 1, And in the denominator, I have a conjugate times a complex number times its conjugate. So I know this comes out to 25. We just did this problem over here. For the numerator, though, I've got real parts from my first and my last. So I'm going to have 6 plus 20i squared. So that's really 6 minus 20, or a negative 14. And for my imaginary numbers, that's going to be the inner and outer numbers, which is negative 8 and negative 15. So negative 8 and negative 15 is negative 23i. But really, if I'm dividing by a real number, doesn't that mean I'm just dividing each coefficient by the real number? And this is the power of using the complex conjugate. It allows us to change a division problem with complex numbers into a division problem with real numbers. And really all we need to do is divide each of these coefficients by that real number. So it makes division very straightforward, very easy for us to work with. So the last thing I want, or the next to last thing that I want to talk about is the idea of powers of I. We know that I equals the square root of negative 1. And we know that I squared is really negative 1. We've seen this a couple of times. Well, if I had I cubed, well, that's really I squared times I, or negative 1 times I, or negative I. And if I were to have I to the fourth, then that's really I squared times I squared, or negative 1 times negative 1, which is a positive 1. So once I know this, if I were to look at I to the fifth power, I know that's I to the fourth times I. But that's just really 1 times I, or I. I to the sixth, well, I can do the same treatment. Well, I've got I to the fourth times I squared, so 1 times negative 1, which is negative 1. And what you'll notice is that, excuse me, that should be a 3. I get 1 times negative I, which is negative I. The numbers repeat themselves. So I went from having an I and a negative 1 and a negative I and a 1, then an I, a negative 1, a negative I, and of course I to the eighth is really I to the fourth times I to the fourth, or 1 times 1, which is 1. And this pattern is going to repeat every 4 cycles, which means I know that I cubed is negative I, but that also means that I to the 7th, and I to the 11th, and I to the 15th, and I to the 363rd are all equal to negative I. Basically, where this number would fall in this sequence, it's got to be one of these 4 values. Well, what's the remainder when I divide this by 4? The remainder is 3, and so that means it's really equivalent to a whole bunch of I to the fourths, 90 of them as a matter of fact, times I cubed, which is 1 times negative I, or negative I. In other words, the remainder from dividing by 4 determines the value. And so that's how we deal with powers of I, because of this repeating pattern. Last thing that I want to talk about is I want to talk about evaluating functions of complex numbers. So keep in mind that we've talked about functions before. I can have a polynomial function like x squared plus 5x plus 6, or I could have a rational function like g of x equals x minus 3 over 2 minus x. And I could actually substitute a complex number in for x. So if I told you that x was equal to 2 minus 5i, then I can evaluate f of 2 minus 5i. So that's going to be 2 minus 5i squared plus 5 times 2 minus 5i plus 6. And so here I've got a binomial. Remember, that's 2 minus 5i times 2 minus 5i. So that's going to be 4. I'm going to have the outer, which is minus 10i. I'm going to have the inner, minus 10i. And the last, which is minus 25, because it's really plus 25i squared. I've got 5 times this binomial, so plus 10 minus 25i, and then plus 6. And then we just combine like terms. Well, 4 minus 25 is negative 21. That's negative 11. Negative 11 plus 6 is negative 5. For the imaginary parts, I've got negative 10i, and negative 25i, so I'm going to have minus 45i. And so this is what you get when you evaluate f at 2 minus 5i. And I can do this direct substitution and use the arithmetic of complex numbers that we've talked about earlier in this video. So I want to finish with this last example. So if I told you that x was equal to 3 plus 4i, and I want to know what g of x is, I'm saying, what is g of 3 plus 4i? Well, this is going to be 3 plus 4i minus 3 over 2 minus 3 plus 4i. So my numerator is just 4i. My denominator is 2 minus 3, which is negative 1, minus 4i. And this is where we introduce the conjugate. Because I'm dividing by a complex number, the conjugate only changes the imaginary part. The real part stays the same. The imaginary part changes sign. And whatever I do to the bottom, I must do to the top. So now I want to multiply. Well, if I take 4i times negative 1, that's negative 4i. And 4i times 4i is going to be minus 16. In the denominator, I have negative 1 times negative 1, which is 1. I know that my inner and outer terms are going to eliminate each other. It's the whole difference of squares idea. And negative 4i and positive 4i give me a negative 16i squared, or really plus 16. So I end up with negative 4i minus 16 over 17. Or I could say that that's negative 16 seventeenths minus 4 seventeenths I. The idea of working with complex numbers allows us to finally address what happens when we don't have real solutions to equations, to functions. It allows us to come up with a system of finding equations for these functions. It allows us to graph these points as points in the XY scale, the real and imaginary scale. We certainly can do arithmetic with these complex numbers, adding, subtracting, multiplying, dividing, even raising them to powers. And we have the ability to substitute them into functions, just like we substitute real numbers into functions. Complex numbers are a very powerful tool, and they're used throughout electrical engineering. They're used in many real-world applications, even though they're just imaginary. So once again, this is Mr. Potter. Thank you for watching. Have a great day.